Yes, it is perfect.
Yes, Alexandra, because we have fled out of the time, please, and we have already listened the presentation from Professor Markovsky. So please skip some introduction slides if you can't, and it would be very useful to see the real method that you have provided. Okay,
Okay, yes, I'll try.
so make it more quick as you can. Thank you.
Yes. Dear colleagues, today I would like to talk about a secure cloud computing method for rapid implementation of cryptographic data protection in IoT. Today, there is a steady trend of expanding the use of IoT technologies in systems for remote monitoring of the state of real-world objects and their management. Despite the known shortcomings, the use of the Internet as a medium for data exchange in these systems is due to the following factors. Orders of magnitude lower cost, system flexibility, that is the ability to quickly configure hardware, easy of software creation, and a practically unlimited range. The application of remote monitoring and control systems based on the IoT has expanded to encompass technologies for unnamed ground vehicles, video surveillance, and security signaling devices within the security industry, as well as infrastructure lines and facilities at chemical enterprises, among others. Consequently, this expansion brings forth the risk of third-party inventions and attempts to falsify information regarding the state of object or management teams. This necessitates heightened security measures to verify the authenticity of data. To verify the authenticity of data regarding the state of objects and control commands, cryptographic mechanisms such as digital signature standard are employed, primarily relying on the modular exponentiation operation. This operation involves processing numbers with significantly larger bit size than those on the microprocessor, necessitating the execution of millions of processor multiplications. Consequently, calculating the modular exponent on the terminal microcontroller considerably complicates real-time management. One highly effective solution to this challenge involves leveraging cloud technologies, which entails performing the majority of calculations on remote computer systems. However, this approach introduces a potential risk wherein an attacker could gain access to the secret keys of terminal devices through attacks on remote computer systems. This slide presents a simplified overview of implementing a real-world objects monitoring system using IoT technologies. In this system, specific sensors, such as a video surveillance camera, collects information about the object state and forwards it to the terminal microcontroller. Before transmitting the data to the computer control center, the terminal microcontroller employs its secret key to create a digital signature. To achieve this, it performs modular exponentiation calculations, with a substantial portion of the computation being floated to the cloud. This design ensures that the secret key remains practically irretrievable based on the transmitted data. Once the calculations are finalized, the terminal microcontroller generates a digital signature using the result obtained from the cloud, and this signature, along with the data, is then sent to the central computer. Hence, the pressing challenge is distributed computation of the modular exponent lies in designing an organizational structure wherein the remote computer system handles the bulk of computationals. Simultaneously, this system should ensure that based on the data it receives, the actual exponent code remains virtually unrecoverable. The effectiveness of such an organization hinges on two primary criteria: security levels, and computational acceleration. Security levels are determined by the amount of the processing required in the cloud to reconstruct the exponent code from the provided data. Computational acceleration is quantified by the coefficient beta, which represents the ratio of the time required for complete modular exponentiation on the microcontroller to the time needed for the same operation when cloud systems are involved. To address this challenge, various techniques for homomorphic encryption of the exponent code sent to the cloud have been proposed. These techniques generally involve breaking down the exponent code into two components, typically an additive and an additive multiplicative one, with one component processed in the cloud and the other on the terminal microcontroller. Because modular exponentiation algorithms are sequential in nature, the additive component, referred to as Q, processed on the terminal microcontroller typically starts from the lower digits. Both the time efficiency and the level of security are influenced by the bit rate of Q. In practical terms, the bit rate is determined by the required security level for a specific application, which can in turn limit time efficiency. These factors constrain the possible values of component Q, potentially aiding attackers in their selection. The objective of this development is to enhance the efficiency of homomorphic encryption of the exponent code for secure modular exponentiation in the cloud by increasing security levels through broadening the range of values available for the part of the exponent processed on the microcontroller. To accomplish this objective, a secure cloud computing method for rapid implementation of cryptographic data protection in IoT is proposed. This method centers on computing the modular exponent from lower digits. The key innovation of the development method lies in not processing just a single fragment of the exponent on the terminal microcontroller, but rather multiple fragments. To achieve this, once a certain numbers of bits have been processed, the cloud transmits intermediate values of D to the microcontroller. This enables the microcontroller to commence processing partial exponent using the D values received from the cloud. Consequently, the range of possible values for Q expands significantly, leading to a substantial increase in the level of security without compromising the time efficiency. The final result of the exponentiation is obtained by performing a modular multiplication of the initial value received from the cloud with the results of processing on the microcontroller. A formal description of the developed method is given on this slide. The described organization of homomorphic encryption of the operands of the modular exponent is illustrated by the following example. Let the modular exponent be calculated for the following values of module M, A, and E. In the first step, the length of the interval h equals 5 is selected. The number of intervals k equals 3 is calculated. The values q0 equals 3, q1 equals 0, and q2 equals 2 are selected. The code q equals 2051 is calculated. The next stage determines the encrypted representation of the square root of the exponent L, which is calculated in the cloud. Next, the values A, L, H, K, and M are sent to the cloud. The L code is then processed in the cloud. The result of R, the values of D1 and D2 are sent to the terminal microcontroller. The value P is calculated on the terminal microcontroller. In the process of obtaining D values from the cloud, the calculation P is performed. The final result of the modular exponentiation is formed by the modular multiplication of the result obtained from the cloud and the result of calculations on the microcontroller. P equals 1303. In the provided example, the microcontroller processes 5 digits of the exponent. In conventional methods, when processing 5 digits, the value of Q cannot exceed 32. However, with our method, the actual value of the Q component is 2051. This example vividly illustrates that the application of our developed method significantly expands the range of possible Q values by orders of magnitude. Notably, using this proposed approach, the effort required for Q reconstruction increases by 128 times, while the computational load on the microcontroller remains constant. The effectiveness of the proposed method is assessed based on the previously mentioned criteria. Security level is gauged by the resources required for an illicit attempt to recover the secret code of the exponent. It's assumed that the attacker has a degree to access to the remote computer system, meaning they possess knowledge of all the data processed there. Furthermore, the attacker is privy to the actual result of the modular exponentiation, which they can readily obtain by monitoring data exchange over the internet. The analysis conducted reveals that the most efficient strategy for reconstructing the E code involves the attacker selecting values for the Q code. The selection criterion is based on the equation a to the power L plus Q mod M equals a to the power E mod M. It's assumed that the number of digits of the exponent processed on the microcontroller is nu. In known methods, the maximum search volume for the Q code is limited to 2 to the power of nu. Unlike other methods, our approach involves transmitting K intermediate data from a remote computer system. This unique aspect allows us, in contrast to conventional methods, to process the Q code from K points. Consequently, the value of the Q component greatly surpasses the actual number of digit nu processes on the microcontroller. This considerable expansion of the Q value range significantly heightens the difficulty for potential attackers attempting to recover the real exponent code. A thorough analysis has shown that the number of certain options increased by a factor of theta, with the numerical value of theta calculated according to the following formula. For practical applications, with typical values of n, nu, and k, and using a 32-bit terminal microcontroller from the ARM company, the value of theta calculated by the formula, which quantifies the increase in certain volume compared to known methods, equals 10 to the power of 37. In practical terms, this means that when utilizing the developed method, a substantial advantage is attained in terms of security levels. This advantage offered by the developed method can also be translated into computational acceleration. In essence, it implies that with identical security level requirements, the developed approach can significantly enhance the speed of calculations compared to known methods. For instance, consider a security level specified as requiring 2 to the power of 64 enumerations. In conventional methods, 64 bits are processed on the terminal microcontroller to achieve this level of security. However, with the developed method, the same level of security can be reached by processing only 16 digits. Therefore, in this example, our method enables a fourfold acceleration of calculations while maintaining the same security level. You can see the conclusion on this slide. The developed method allows you to significantly increase the level of efficiency and more specifically the level of security due to obtaining intermediate values from a remote computer system. Thank you for your attention. I'm glad to answer your questions.
Thank you for this very nice presentation. Are there any questions from the audience? Yes, Pericles Giannaris.
Would you please describe simply like an application in everyday functionality? Like, for instance, can we use this with some cryptography algorithm for encrypting text messages or something like that? Thank you.
Actually, first of all, the areas of application of our development, it can be security alarm and video surveillance system, like I said before, remote control of production lines, infrastructure facilities in vehicles. No, that is industries that require increased security in the process of confirming the authenticity of data.
Thanks.
Okay, so thank you for this. Any more questions from the audience? Okay, so thank you for the presentation. And if we could all join the special